Hi everyone, let's get started. Uh, my name is Kannan. I'm one of the co-founders at Yugabyte, and my pleasure to welcome you all to the next episode of YugabyteDB Friday Tech Talks series. And this is coming from engineers for engineers. And today I have with me Raghavendra T. Would love for him to introduce himself and then jump into the topic. He's been on this series earlier last year, talking about the packed row format, if I'm not mistaken. So TK, welcome back.
Thanks, Kannan. Hi, everyone. I'm Raghavendra. My initials TK. I'm one of the managers at Yugabyte. I lead the parts of the storage team here at Yugabyte. And let me get started right away. So I hope the screen is visible to everyone. So today we wanted
TK, it's good.
Today we wanted to discuss the network and on-disk compression strategies that are available in Yugabyte DB and how customers can actually benefit from this. Right? So I'll start with the network compression topic. So what's the motivation now? If you look at cloud providers across the board, they charge for data transfer that happens across availability zones, across right? And for products like databases where there's a huge amount of data that's actually transferred between these ACs and regions, these costs can actually be quite significant, right? And if you take, for example, Yugabyte, it's fundamentally a distributed database, and it has tons of traffic that spans across nodes, be it the communication between like the IP master process and these servers across different nodes, or heartbeats that span different nodes, or like the raft replication of the data that needs to be replicated in ways across different nodes, or the reads that actually need to collect the data from different tablets, aggregate it one place, and return to the query, right? So there are all types of access patterns that can benefit from compression, but the biggest benefactor is, of course, the raft replication of the data, because that typically accounts for a huge chunk of the data transfer, right, in terms of the volume and things like that. Yugabyte DB has incorporated compression libraries for its network transmission and data transmission. How can one leverage it, right? So we have a gflag enable stream compression. By default, it is true, and that's used to disable it if customers feel like they don't need it and things like that. In terms of the algorithms that are supported, we do support gzip, snappy, and lz4 for compressing the network traffic, and yeah, that can be changed by the gflag, the stream compression algorithm. So we'll take a look at some of the experimental data to figure out, hey, which one of these compression mechanisms should be used, can be used, and under what circumstances. So I'll go over the suspense experiment numbers to begin with. There's a lot of data, so I'll present some of the fundamentals. Basically, the first experiment focused on the reads, right? So it ran a bunch of selects on 24 connections. Under the hood, we had generated enough data on these key tables, and this is your suspension read benchmark. And the second experiment is the suspense write benchmark, which inserts a bunch of data, and in this case, we used parallel connections to the same 250 tables, right? This is roughly about the data that we ingested, and we actually ran it with the various network compression, stream compression algorithms, and with no compression, gzip, snappy, and lz4. If you look at the latency profile across all these, let's focus on selects for the time being. gzip has the highest latency, and you can see That's because the compression library uses a lot more CPU compared to no compression or some other compression strategies, right? And as such, the latency is a little higher. And that naturally translates to slightly lower throughput compared to the rest of the algorithms, right? But if you look at the benefit of using gzip, you can see that in the network bandwidth columns, right? This is the amount of network traffic was received by the node, and this was network traffic that was sent, right? So if you look at the total amount of network traffic, it is significantly less in gzip compression, right, compared to some of the other schemes, and that's where like the compression savings is about 46% at least in the sysbench. Again, some of these numbers are dependent on the schema, but for this schema, wanted to showcase that hey, gzip sort of like beats the other compression models. However, there is a cost associated with it, right? But if you look at without compression versus with compression, yeah, I mean, gzip saves you about $917. We sort of like extrapolated the results of these experiments to say, hey, if you have so much traffic per month, um, how much would the network cost savings be, right? And with gzip, there's going to be a significant cost savings, around 900. And that's for selects.
Yeah, maybe actually why don't you finish the inserts and then I have a comment.
Yeah. So for inserts, it's roughly similar. You can see the latency with gzip is slightly higher, and that translates to slightly lower throughput. Again, CPU is slightly more, but the compression ratio is pretty much the same. In the case of inserts, again, the RAF payload gets compressed, and the compression savings is pretty much 48 or around the same ballpark as selects, right? So again, compared to no compression, there's a huge amount of savings with the gzip, and relatively less savings with some of the other compression models. Kannan, you had a question.
Yeah, I was going to say two things. Like I think one you alluded to, which is that the compression rate is going to be very schema dependent or payload dependent. For example, you can imagine that if you had a fairly large JSON payload in your row, or mostly like text data, those should be pretty compressible even with the LZ4 scheme. It's possible that sysbench has a little bit more binary data that LZ4 is not able to do a good job. So that is one observation. The second, like if you look at the insert and the CPU column, right? In this particular case, looks like we were running on a setup where CPU is already pretty hot in the no compression case. You're already kind of pushing the CPU close to 82%, right? So at that point, like any additional resources needed to do the compression is going to start a little bit non-linearly impacting the system. Whereas if you had enough headroom, like if you ran your system not so hard, but maybe at 60 or 70% CPU utilization, it's possible that the latency impact is not like 1.5x, but maybe like 10 or 15%. But yeah, it just goes to show that it's these numbers are very workload dependent, and how close to hot you're already running the system. In which case, is there really enough headroom to do this compression and decompression?
Thanks for reinforcing that, Kannan. So yeah, I mean, it ran PPCC, and again in this case as well, PPCC workload we sort of like run it with very high load on the system. Although in this case we ran it with relatively lower this thing. So when the system resource utilization is lower, then even then, I mean, in some cases, yeah, gzip is showing a little bit higher latency, right? And yes, to Kannan's point, it may or may not matter to workload. It's entirely schema dependent. So definitely it would be good to check in cases if the gzip compression provides the benefit and in terms of the latencies, your workload is okay with reduced latency, or if the latency doesn't even matter for that particular workload, right? But otherwise, I'll go to the next slide. So what strategy?
Okay, one question from the audience is, at what granularity is the data compressed? Is it a streaming-like compression, or is it something that's compressed one row at a time?
So in terms of the granularity, I believe it's at the message level. Like I mentioned, the network compression applies to all kinds of communication, not just the data. And so even the messages that are transmitted are compressed. So it's at the message granularity, and message can be more than one row in some cases.
Yeah, it's basically the RPC traffic itself is compressed, and if it's a batched insert, then it's spanning multiple rows. It could be a multi-row select. So it's almost like payload independent. Even the internal wrapped replication messages are compressed and so on. Yeah, thank you.
To sort of like summarize, like, hey, which compression algorithm to use, I would say it's dependent on two main factors. One is the deployment topology, and the other one is the workload pattern. For multi-AZ or multi-region deployments, where network costs are quite high and they tend to be, in some cases, much bigger than your compute cost, we believe that gzip is much better suited, even though it can impact latencies of certain queries, right? However, in single AZ deployments where network cost is not really a problem, you can choose to use LZ4, or in some cases even not care about enabling string compression, right? And for YBM, Yugabyte managed offering that Yugabyte offers, we use the above strategy. So for if a customer deploys a database in multi-AZ region, gzip would be the default network compression, string compression strategy they would get. If it's a single AZ deployment, then network compression is disabled, okay, because we want them to get the best throughput. And in terms of like, hey, when can I use it? The feature actually has been there for a while, since 2.6.3 release. Several months ago, in fact, more than a year ago. But there were some caveats, so I just wanted to put it out there. There might be some customers who are on really old builds of Yugabyte. The versions prior to 2.6.3 do not necessarily have the code to interpret the data. So if you want to enable the feature of network compression, make sure all the nodes in a cluster are at least 2.3 or above, and then you can safely enable the compression as well as the compression. But most recent clusters, you can feel comfortable to actually just
maybe just as one data point, I was looking up, say, just as an example, in Google Cloud Provider, what the network costs are, and this is just like a quick search. So, pardon me if I'm incorrect on this, but from what I'm interpreting, it's like interzone traffic. GCP charges about 1 cent per gigabyte. For inter-region traffic, it's dependent on which continent and so on. So Europe is about 2 cents per gigabyte. Asia is about 5 cents per gigabyte. So it's there is some variability. I haven't looked at other cloud providers, but I thought I'd share that.
Thanks, Kannan. So next, I want to touch upon storage compression. And again, network is one cost. The other cost is storage from compute and in workloads where there are huge amounts of data, terabytes per node. They would benefit a lot from storage compression. That way, customers can actually pack more and more data into a single compute node. For example, so Yugabyte, the storage layer, the DB layer, stores the data in SSD files, and uses the RocksDB library, right? So it supports the compression schemes that RocksDB supports. For compatibility, we have mostly enabled Snappy, zlib, LZ4, and compression schemes. How can one leverage it, right? So there's a G flag, the server G flag compression type, and if we set the value to one of these, that particular compression type is going to be used, right? Now some quick notes on this G flag. I got to give it a valid value. Changing the flag on an existing database is supported, so you can actually switch from one compression scheme to another. And it only takes effect only after the nodes are restarted, right? So as a result of that, if you look at a tablet's data, it can span from one compression type to another, and compactions that happen naturally as part of additional data, additional time. Compactions would eventually produce new files that are appropriate to the current compression structure. So they'll get rid of any files that have been possibly written with the older compression scheme. So now,
two more questions. The first question is it's related to the network compression feature. So if you're running cross-cluster, the X-cluster capability across two Yugabyte clusters, can you mix network compression traffic for internal versus external? In the case where, for example, local, it's better to do LZ4 and gzip for the other. It's a great question, and I don't think I know the answer offhand. But
I don't think we have an knob for that. But yeah, I'll double check with the team and get back. That's a great question because definitely the cross cluster stream is a dedicated stream, and there are some knobs to control the rate and other things. But I don't think we have exposed the compression knob there as well.
We'll definitely post back on that LinkedIn thread itself the reply, because I'm sure the right people in the team can confirm the answers. So yeah, thanks for the question. One other question, now this is back to storage compression, PK, that's being asked is, are you using compression of encrypted data? And if so, can the encryption reduce the effective compression ratio? So that's a great question too, but if you want, we can answer it.
Yeah, I think compression and encryption, they typically don't go well together. I've seen it in previous solutions as well. The experiment, sorry.
Yeah, maybe I can take the answer. So actually, we are not compressing encrypted data. It's the other way around. We compress our blocks and then encrypt it. Our encryption is size preserving. So if you have 4K, after compression, if you end up with a 4K block, then we encrypt it and it stays a 4K block. So we don't suffer from this concern that we are reducing the effective compression ratio. So encryption is almost like the last step. We kind of do prefix encoding, then compression, and then encryption.
Thanks, Kannan. Yeah, most of my experiments the data that I was referring to was without compression. So if I look at the results from the TPCC experiments, showing the 250 warehouse experiments and 2,500 warehouse experiments, but they scale pretty much linearly. And you can see the size of the SSD files on the cluster, sum of the sizes of all the tables, right? With the snappy compression, the storage cost was about close to 30 GB per node. With zlib, it was close to 20 gigabyte per node. If you didn't compress it, you would get close to 60 GB per node, right? And if you look at the TPCC performance numbers on transaction throughput or efficiency, there's not much of a difference, right? Because in the mainline code path, TPCC is pretty much working all of the in-memory structures and cost of compression doesn't necessarily show up to the user workload, right? Um, so some of the conclusions is that, I mean, even though I just showcased the TPCC data, we also ran like a bunch of other workloads like Cassandra key value workloads too, and a bunch of other uh, workloads that some of our customers provided. Um, Across the board, we noticed that zlib compresses the data quite a bit, right? And it does provide a lot of space savings compared to Snappy. Um, but a couple of things we did notice is the CPU utilization with zlib is slightly higher compared to Snappy across the board. With TPCC also we could see a little bit variation, but more read-intensive workloads we did observe slightly higher CPU utilization, which resulted in like latency delays for feeds, right? And so that is one of the other aspect. Again, from our standpoint, we have left the default as Snappy so that it sort of like caters to most workloads. But if you do want to benefit from better compression and the workloads are not as latency sensitive, it would be better for you to evaluate zlib for your test workloads and then even adopt zlib if you want to get additional storage savings, right? We did recommend it, and a couple of customers have changed the default from Snappy to zlib for their deployments. But yeah, some of the side effects that you need to be aware of is that sometimes compactions can actually take significantly longer. But yeah, so compactions are background activities, so they may not necessarily impact the workflow, right? However, the read latencies do take a little bit of the hit because if the I mean, the read request needs to actually decompress the data, right? So, uh, so one of the additional aspects about storage compression that I wanted to talk about today is the delta encoding scheme, right? As I mentioned, Yugabyte already uses the RocksDB as its storage layer. And RocksDB provides the support for prefix encoding, right? Like if there are a bunch of key value pairs and the prefixes are sort of like similar, then you can pretty much benefit from collapsing the prefix and not repeating the prefix across different key value pairs, right? Now, if you look at the SSDs in RocksDB, they're sorted, and so there is a good chance that a number of the key components get repeated across the board. Right? And the sorted strings can benefit a lot from the prefix scheme, right? One of the things about Yugabyte is I put the Yugabyte RocksDB encoding diagram here just for reference. So the first part of the key, so the top part is the key, and the part is the value. So value. The key consists of a doc key, consists of hash columns or the range columns, and then the subkeys, and then we also have the doc hybrid type, right? So in the case of the custom format of Yugabyte, it's possible that across different key value pairs that are stored in SSDs, it's not just the doc, it's not just the prefix or the doc key that's similar. There are parts of the subkeys that could also be similar, and so Yugabyte implemented a custom three shared parts encoding scheme to actually take advantage of the fact that even the subparts of the key would actually be common, right? And so we touched upon how one can use the scheme. It's again controlled by a T server, a G flag, or
maybe
regular.
TK, you might have made the point, but maybe I just wanted to, on the previous slide, mention one thing. The context of this delta encoding is essentially at the block level. Like imagine Yugabyte as part of a flush or compaction is producing a new SS table file. An SS table file internally consists of blocks. We try to keep the blocks about some configurable size. I believe the default might be 64 kilobytes. But within these blocks, keys are stored in a certain sorted order. They may be stored in the internal hash value of the adjacent keys, or they may be stored in, if it's an ascending column, it will be stored in the ascending order of the key. So because the adjacent keys have a lot of common overlap, a lightweight scheme like some form of delta encoding that tries to capture the delta between the two adjacent keys in a block and encode them in a way is very space effective. And just wanted to mention one more point, that this space savings is not just on disk. Our in-memory blocks themselves keep blocks in this delta encoded format, right? So it helps keep the memory footprint also very low. And now we are talking about two variants in this delta encoding scheme. One is a very simple prefix-based delta, and the other one is this more, Yugabyte optimized delta scheme. Thanks, Steve.
Thanks. Yeah. So yeah, I mean, to actually leverage the scheme, you can use the T-server flag, regular tablets, data block, value encoding. The default is the shared prefix, which is what comes with RocksDB, and the three shared parts is the scheme that Yugabyte has added. So we've left the default as shared prefix in the older builds. Starting from more recent releases, we have switched the default to three shared parts. And again, one of the reasons we only, even though it was available in the older build, but only changed recently, is that if a customer is upgrading from a much older build, say 2.0 or 2.4, we didn't want those clusters to get it immediately, because the code to actually handle this encoding is not there in the older versions, right? So in the middle of an upgrade, if one node sends in the new format and the whole node doesn't know how to interpret it, it's going to result in failures, which is why we leverage this framework called autoflags. I don't know if we have talked about autoflags in the past, but with that, Yugabyte now has the capability to enable a feature only for new installations, right? And so we leverage that feature. And so if you have a new cluster that is starting up in 2.16, then the default will definitely be three shared parts encoding scheme. However, if you have an older cluster and you upgrade to 14 or even 2.16, the default remains the older default of the shared prefix, right? Now, and quickly about
and TK on this point, the previous slide, to talk about, for example, how three shared parts encoding is the default for new clusters from 2.16, right? And just to be, this applies. Question is this a default for open source clusters also? Like, is it a dynamic? Like, is it using the new auto flags mechanism to automatically go to this new default, or is it more something that's available through the Yugabyte Anywhere platform? Do you know offhand?
Yeah, so it definitely uses the autoflags framework, and as far as I recollect, Yugabyte Anywhere is definitely supported. For the open source, I don't know if we have a clear signal of whether this is an install versus an upgrade, but that's something that I can follow up with the team as well. Okay. Like if would open source, would a new open source cluster have three shared parts as default?
If it's using the autoflags framework, then yes, it would figure out that it's a brand new cluster. One other question, TK, from the audience is and maybe this is a reference to the picture you had on the previous slide. Are the blocks, is it sorted on the whole key, or do the parts of the key get sorted separately? he's referring to the doc key, sub key, and the time. Right, there are three components of the key, and I guess the question is, do you sort on the whole key, or do the parts of the key get sorted separately? No, logically, think of it as a concatenated key, and you have to sort on the whole key. But net result, what would happen is it would like the doc key becomes the first dimension of the sort, and then within things that share the same doc key, you would sort by sub key, and then within things that share the same sub key, you would sort by the the hybrid timestamp of the chain. So there are two ways to think about it, but yeah, it is sorted on the whole key.
Yeah, I mean, the SST is sorted out. So quick look at hey, what are the benefits of the two types of encoding, right? So in this example, we actually looked at the TPCC workload and what were the benefits of the two different types of encoding schemes, along with the compression scheme that I talked about earlier, right? As you can see, the three parts encoding produced much better compression. It reduced the payload quite a bit compared to the shared prefix encoding scheme, right? And this data also shows that we also actually also get the compression benefit of the regular compression libraries as well, right? So they are additive in this case. So and Kannan mentioned the data in the block cache is also in the encoded form. So the compression scheme, the delta encoding scheme that you select would not only help reduce the disk footprint, but it also helps reduce the memory footprint. Right? But it does pay. It does translate into the cost into the reads or scans. Now every read needs to actually first decode this thing and then actually give it to the higher layers, right? And so again, you have to not just look at the storage savings, but you should also look at would it impact the latency if you're working, right? But overall, if you are interested in actually reducing the footprint of your storage, you should definitely look at making sure that three parts encoding is enabled and you set the right compression type for your storage, right? I have a couple of references, but I can quickly switch over to a cluster and showcase a couple of space savings and how they can observe it, kind of a thing. So I have a cluster here that has some workload going on.
So TK, how much time do you anticipate needing?
Just a couple of minutes, but if you're over time, you can probably skip this.
Sounds good.
Yeah, so you can see it's still getting a bunch of reads and writes. And in this cluster, I believe we have enabled zlib, and you can see this cluster is actually getting 10x compression ratio, right? And compressed data is about 300 gig, and compression is about 37 gig, right? And yeah, the compression type is zlib in this case. Yeah, I mean, I just wanted to showcase a live cluster and sort of like how you could compare like how much compression you're getting, kind of thing. We already do showcase like, hey, if it is uncompressed, how much would the size be and things like that, right? So you can actually understand the benefit of the compression scheme just by inspecting these either on the nodes page, or you can go to the master leader and the tablet servers page.
So TK, one question is, you talked about like zlib giving some extra savings, but it does impact the compaction times and all that. It's so maybe that's why we left Snappy as the default. There was a question on storage compression. Have we considered LZ4?
Yes. So one second. Yes. So LZ4 was part of the thing. I didn't include the I didn't include the data in the graphs, but yes, for these workloads, I don't think we observed significant gains.
Compared to Snappy?
Compared to Snappy, yeah.
It's
almost the same.
And then one other point to the earlier question on can cross-cluster traffic use a different compression setting compared to intra-cluster traffic. So one of the engineers confirmed that that's not something that we support today, but could be an enhancement, right? But one thing I wanted to mention is like the two clusters that we are connecting using X cluster, they could have different settings, and depending on where the connection originates, that cluster setting will be respected. But the ask is reasonable, saying, hey, within the same cluster, maybe we should allow for inter-region traffic to have a different setting compared to intra-region traffic, right? So that makes sense. I think we should look into it. I also wanted to mention one thought that one topic we didn't cover is the compression of traffic between the application, the client itself, and the database. And that's a little bit on the API dependent and driver dependent. At least for YSQL or Cassandra API, all the drivers do support an option to run with compression on, but I don't think it is the default. So that people should consider turning on compression, and these Yugabyte's YSQL API is compatible with the Cassandra wire protocol. It's based on that, and so we support compression as long as the app sets the right parameters in its initialization code. On the YSQL side, I don't believe I could be wrong here, but I don't believe the various YSQL drivers like the JDBC drivers or PG, all of those. I'm not aware if they support compression, but that's something that potentially we can look at. Do you know TK offhand or SQL? Okay.
Sorry, no. I won't check.
Did you have anything to cover else?
No, that's mostly what I had.
Yeah, so let's bring this talk to a conclusion. Thank you everyone for joining today and asking a great set of questions. And we look forward to seeing you all next week on another topic. And yeah, thanks again. Have a great day and weekend. TK, over to you.
Yeah, thanks everyone. Yeah, here to talk about this topic. If you have follow-up questions, please do post that. We'll definitely get back to you. That's it. Thank you.